I would like to go back today on a few of the slides that I have shared with you last time. And I would like to go over them again because I received a number of questions from some of you. And I would like to tackle these questions so that, we are clear about all these particular components that I have described last time. So let me go here. Okay. So last time we spoke about the convolution neural network structure and what it entails. Some of you, have grasped the material. Some of you have already seen it, from some other courses or some other type of problem that they have encountered. But I would like to go quite briefly on some of the aspects for this convolution neural network and why we have received these questions. Before I do that, I just wanted to remind you that we still have one full week for the assignments. I urge you to start working on it if you haven't started yet. And if you have any questions related to certain components of the assignments, please direct your questions to my TAs. I have mentioned in the assignments whose TA to contact when you have a particular question on the assignment. So we will have also our second quiz on Monday, and it will be exactly the same time as before. So I will send an email to remind you of the exact time, at what time it starts. So there will be 2 periods for the quiz, and it will include almost every material that we have seen so far. Most probably material that happened after the first quiz material. So, and it will include material that we are seeing today. And because of a number of questions that I received from the students, and because the lecture was not recorded last time, I provided the annotated slides. I hope that it helped a number of you. It's visual, it's straightforward, but I would like to go over a few items today. And I would like to conclude about some of the aspects of convolution neural network. I will also try to speak a little bit about recurrent neural network before we start on a new subject next week for this course. Mahmoud actually has made an excellent tutorial last week, tutorial number 4. Ravi has also been waiting for your questions during the office hour. There will be another office hour on Tuesday as well by Mohita, and Mahmoud will go with you today over a 5th tutorial introducing PyTorch and some examples related to PyTorch. Okay, so let's go back. So this is a visual representation of one of the earliest convolution neural network, which was proposed by LeCun. So you can see in this particular neural network, you have an input there and you have an output here. So the system was possibly aiming at classifying up to 210 alphabets. And then the system has gone through several what we call feature maps. So these are higher levels of deep learning. And you can see that the system goes from a larger dimension to a smaller dimension at the end, but with larger component, with a larger number of components, as you can see here for this particular representation. And this is due to the fact that we are presenting the system with a number of kernels or filters, and then these type of filters are going to be sampled using some what is known as the pooling type of operation. I will go over it very, very quickly. And then the system goes another level of convolution, another set of filters, as you can see here. So this is the second set of filter in the convolution number 2, and then subsampling as well. And then the system becomes fully connected, and then it goes and it utilizes a number of activation function, namely the Gaussian connection representation, which are the activation function that we have seen similar to the multi-layer perceptron. So this is the first image here. So this is another representation here for the convolutional neural network, it's very, very similar. So you have what we call N channels. So I would like you to understand very well this type of dimension. So what it means? So it means 28 by 28 by 1, which means it's one single layer here, but it's 28 by 28 matrix for representing 2. In the RGB system, in color type of pictures, we will end up with, instead of this one, it will be 3 for the RGB, because we have 3 channels for each one of the colors. And then we are going through what is known as the kernel particular components, which is the convolutional one. So there are several type of kernels, several type of filters here. Then there will be an operation known as the max pooling. So you can see also the max pooling. You have a certain type of dimension here. You have this kernel dimension as well. What it means that it is a kernel with 5 by 5. So this is 5 by 5 kernel for this particular system. And here we have channels for this particular type of system here. And as you can see here, so there is the dimension of the various type of kernels. So you have n kernels here, and each one kernel has 5 by 5 dimension. So what we do, we end up with a system that is going to have a dimension of 24 by 24 using certain type of slides. So when we define a kernel, so we define by its dimension, we define also by the number of channels, which is number 1 here, and then this provides you with the final outcome of the systems. And then you transmit this channel through a max pooling operation, and then we repeat this convolution here with another 5 by 5 kernel to give us an 8 by 8 system times n2, which is the number of channels. So I would like you to know here that this 12 by 12 by n1, its operation with these 5 by 5 kernels and with n2 type of channels. So there is n2 type of filters. So these kernels, so there are n2 of them. And then this system provides us 8 by 8 by n2, which is the number of channels or the number of kernels. And then there is max pooling, and then we flatten the network to provide us with this final type of output. So this is an excellent type of representation for this particular system. So that's what I wanted to share with you here about these type of dimensions, so how they are created through these type of kernel. So we have spoken about, CNN versus feed-forward neural network. Why CNN are excellent type of systems? Because we are representing regions of the pictures rather than looking at the pictures as certain elements of pixels that for which, the region between one pixel and one pixel is not expressed in this particular representation of the feature. So what we would like to do here, we would like to provide certain type of deep learning behavior where the system is extracting as much information as possible from a pixel and its neighborhood. So you are talking about regions of the image rather than pixels of the region, as we often do when we are confronted with the neural network system. And of course, this particular system, ultimately, when it is becoming connected at the end of the layer, it's going to be represented by one single vector. So this is, the rationale behind using convolution neural network. Again, for 3 color channel for an RGB, so you have this representation. So you have the red, the green, and the blue, the RGB. So this is the width, this is the height, and this is the 3 color channel. So this particular system could be represented as 4 by 4 by 3. Okay, so this is the representation of what we call the tensor input. So tensor is an image or is a matrix in dimension 3. So we have the matrix and we have a tensor. So the tensor could be of dimension 3, it could be of dimension n. We could have 4D dimension tensor, we could have ND type of dimension tensor. Okay, so this is what we would like to have. We would like to have a deep learning type of behavior of the system, so that the system at the end is providing us with, I mean, classified or the most likelihood of the class that we do at the input level of the system. And the major difference between an MLP and a CNN is the stage that we do between this input, between the image and these particular input. So for the system that we have deep neural network system, so there is a whole deep layer in between here, between the image and the input that we are going to give to the system in the fully connected. For the system in the MLP, you start directly with an input where this image is translated into a vector of a number of rows. So these, I mean, we spoke about it, the major characteristics of a convolution neural network. So you have the layers, you have regularization, you have activation function, objective functions, optimizers. We have gone through this and it is self-explanatory. So the convolution for the CNN, I mean the convolution layer, so you have the pooling layer, you have the dense layer, the flattening layer. So these are the major components of the system. And this particular part could be repeated several times. So this could be repeated several times for the deep learning structure before we go to several times. Okay, so several times. So we could have sometimes, I mean, one convolution layer, very difficult to have one convolution layer, but mostly we have 5, 6, and there are in some example up to 100 convolution layer for a particular system. So last time, so I showed you this particular picture and I would like to repeat it because it's very illustrative and it reflects what we do, what we know by convolution. So convolution is no other than taking a region of the image and convolve it with a filter. So in this particular case, the filter is yellow. As you can see, the filter is scanning the image from the top to the top left to the top right, and then it slides below from the middle left to the middle right, and then from the lower parts of the image from the lower left to the lower right, and then it builds these particular type of components. So that's what we what we represent by convolution. It's exactly the same thing as the convolution of a signal. I will show you in another set of slides how we can represent it mathematically, but this is a visual type of representation for this particular image. And then we do this for all the type of filters that are required for that particular system. So the system is going to give us a certain type of output, and for each one of the layers there is what is known as the depth. For this particular type of image, we are going to obtain for each one of the filter 1, we are going to have this layer. For filter 2, we are going to have another layer here. For filter 3, we have another type of layer, okay? So for filter 2, so this is filter 2 here, and then filter 3 here, okay? So that's filter 3. So this illustration for this particular slide is for one single filter, okay? This is another image. I mean, this is a good way for representing an RGB. I'm repeating this type of images because they are very illustrative and it shows you exactly how we compute the output of an image with 3 channels. Namely, the 3 channels are the colors with one particular filter. So the filter here is the filter that is going to go through this particular channel. Usually, the filter have the same values. So in this particular example here, the filter is different for each one of the channels. But usually when we are doing the CNN, all the filters have the same exact value for one particular filter. If we are putting more filters, then these particular type of filters are going to be different values. But this is an example illustrative of how to utilize for various type of channels, various type of filters, how to obtain a particular type of the output system. Okay, so here you can see the filter is scanning the image and then from one side to the next side. And as you can see, these particular elements here, the zeros and the zeros here, so they are what is known as padding. I spoke about them last time. So let's look here exactly what we mean by the input and filter. So these images are very important to understand what we are doing. So we are subjecting the images, the first image, which has a 3 channels, okay? So the 3 channel is expressed here. The 6 by 6 is the dimension of this particular image here, and this is the 6 for the number of column, and the 3 denotes this particular number. And then for each one of the filters, we are going to replicate the filters for each one of the channels. So this is the image that a number of you asked me to repeat it because they did not understand it well. It was only annotated. So as you can see, for each one of the colors, for this particular filter, which is, only 3 by 3 filter, but it is being repeated 3 times here. So what it means 3 times, it means that this filter has 3 type of layer. So we present one filter. So when we say a filter, that particular filter is replicated for each one of the channels. It doesn't mean that we have 3 filters. No. So this is one filter. As you can see, 1, 0, minus 1, 1, 0, minus 1. Exactly the same filter is applied to each one of these particular inputs. So this is filter 1. And this particular filter 1, we are going to have this particular convolution here, plus the particular convolution here on the second channel, plus the convolution on filter 1 for this particular part, and then we add them up, similar to what we have seen it here. So here, if we would like to implement this image to the one comes next, we have to have the exact same components of the filters. So then we are adding all this particular value so that we have one particular component for that particular filter. So this is what we have. So this particular convolution 3 times this convoluted with this particular filter is going to give us one particular output here. This particular output is 4 by 4. Why it's 4 by 4? Because the sliding here, the sliding of this particular one here. So we have one slide here, second slide here, third slide here, and then fourth slide here. So when we are sliding the window of the filter, which is 3 by 3, we end up with 4 elements. So for each one of the slide, we are going to compute this particular number, and of course, after we do the summation. Exactly the same thing is applied to another filter which has other type of characteristics. So here, this is another filter, 3 by 3 times 3. Although here, this is, this should be value of 0 because the filter is replicated throughout all the filters. So this should be 0 here, this should be 0 here. So the exact filter here is replicated for each one of these particular type of path. So please feel free to raise your hand or to email me, to ask me if you have any question, because your question could be helpful to the other students. So once we have filter 1, once we have filter 2, then we are going to end up with an output for all this particular type of operation of 4 by 4 by 2. So I am repeating this image because it's very important to understand, and this is very helpful if we can apply it and we can implement it for this particular type of system. Okay? So I proceed forward here. As I mentioned to you, for filter 1, we are ending up with this feature map. For filter 2, we are ending up with this feature map for this, gray type of images. So that's how we create this feature map, which are no other than, this is feature map 1 in that image, feature map 1, and this is feature map 2. Okay, so because it goes through 2 filters. So we have here one filter, the one that is sliding, so it gives us this feature map, another filter that is giving us a second feature. Okay. So here, I'm not going to repeat these things, but this is the computation that we did last time and how we do these particular parameters. So a parameter for convolution is the size of the filter. So this is 3 by 3. The number of strides, the sliding from this level here to this level here. So we slide by 1 in this particular example. So we slide from 1. And then the padding. So there are no padding. There are no additional elements around the image. So we spoke about that. And this is how we compute this output of the system, which gives us 4 by 4, which is how to explain this by 4. So it is explained in this particular image. Okay. And then we so move the overlay right on the position so to obtain the second element for the system. So this is an excellent picture to showcase how we fill up all these elements of the matrices, and this is self-explanatory. So for this particular system where we are increasing the number of strides, so also I received some questions about the strides, what it means. So we go here, so we have the first window into the dotted elements. So that is filtered, convoluted with this filter, we obtain number 2. And then what we do, we convolute, so we do stride 2. So this is what it means, stride 2. So we take two steps, two blocks, and then we move the window. So the window is not moved by one, similar to this case. So this is known as the stride of level 2. And this is going to end up with a system that is going to be given by this particular value here of the results of the system, because stride is equal to 2. Remember here, the padding is equal to 0 because we are not adding anything. However, when we are doing these strides, if we go another stride 2, we are going to end up with something that is going here, okay? But here we don't have any value. So we don't compute that value there because we don't have any value here. So the system is not going to do a convolution with values that it doesn't know. So that's why the system is 2 by 2, but we are losing all these particular type of information in the system. So what we do, instead of losing this particular information here, we are going to pad the image by one particular level of what is known as the padding. So the padding here helps us out when we do the strides 2. So when we go here, then when we go another stride, so we go from here. So then the system is able to, so we have, so this is stride 1. So this is the first one here. And then we do stride 2, and then we move here. And then the system is providing us with this particular value. So you can see that we have moved, because the system now has been, started from this particular level, and then this is 0, so we don't lose anything. So this provides us with the padding capability of the system, and it provides us, instead of 2 by 2 now, it's 3 by 3 matrix. And this is for kernel with dimension 3, with size 3, stride number 2, and padding is equal to 1. Okay, so this is what we meant by padding and by striding. So this is a formula to provide us with the number of output dimensions. So here the output dimension is 3 by 3. So that output is obtained by the number of the input, original input, by the padding value for the original input, by the number of filters, the dimension of the filter, and then divided by the stride. And then we add +1. That gives us the dimension of 3 by 3 for this particular type of system. So this is what I meant last time when I spoke about these type of representation. Now the pooling. I received also some questions about the pooling, and I wanted to repeat all of these things so that all of you understand what we mean by that. So the pooling is basically a downsampling. So imagine that our convolution layer has given rise to this particular matrix, but this is still large matrix. So even if we go from 8 to 8 to 5 by 5, still is a large matrix to compute. So what we do, we go and we apply what is known as the pooling. So the pooling is a vector to scalar transformation that operates on each local region. So what we do, we go to this particular, 3 by 3 type of image here, and then we assign what is known as the pooling. So there are several types of pooling. So in this particular case, we take the maximum value of this particular matrix. So that number is going to be equal to 3 here, okay? And then once it slides, this way here, we take the maximum value and we obtain another 3 here. We continue the sliding with the pooling filters or pooling matrix here. So we call it pooling matrix, and it gives us 3. So this is how we are computing the same thing. So we slide now downward with the strides equal to 1. In this particular case, we obtain the 3. And then finally, we go to the pooling layer for the particular system, and we end up with the 3. So, and then we keep, sliding window by window, and here the maximum value is going to be equal to 2, as it is here, and then the last one is going to be this particular matrix here, which is going to be this particular value, which is 3. So this is what we call it pooling. So there are several types of poolings. So there is the max pooling, and then there is the average pooling. And then there is also the dimension of the pooling itself. So in this particular case, so we have a pooling of dimension 2 by 2 with a stride of 2. Okay, so let's look at the max pooling, what we mean. So here we have 2 by 2. So we take the maximum of this 2 by 2, we obtain the value of 20. We take the maximum of, and then we do strides of 2, and we end up in this yellow type of region, and the maximum is equal to 30. So here the maximum is going to be equal to 37. The maximum is going to be equal to 112. So we go from a 4 by 4 dimension, 4 by 4, by 1 in this particular case. So we are using one single matrix here, and then we end up 2 by 2. So in this particular case, we say that we have done a sampling, sub-sampling of the system using max pooling. The same thing for the average pooling. So we take the average of all these elements, and then we assign it this particular number. We take this particular number here, we divide it by 4, so it gives us value of 8. The same thing here, we divide it by 4, so it gives us this number. The same thing here by the integer value of this particular number, and we take this particular value. So that's how we do this particular type of pooling, what we call it also subsampling. So I hope that this is now understood. So this is how we do it. So we have the original input, we go to a convolution, and from a convolution, we go to a pooling. As you can see here, the convolution here for the filters, so you can see that there are 3 filters in this particular case. Although the first image has only one channel, but since we have 3 filters, for each one of the filter, we have a particular output for the system. And then this particular, this particular layer is going to be replicated when we are doing the subsampling for the system. So subsampling, it means that we go into the sampling. So you go from 4 by 4 to only 4 element by 1. So this is, 4 by 4, so which is 16 elements, and here it's 4 elements. So these are the pooling, operations. So it gives us dimensionality reduction. It extracts also dominant feature for the system, the most important features that have the highest values, and they are collected in the pooling component. So this is what we spoke about the pooling, and this is again the example when we are dealing with the multiple filter. So I would like also to talk a little bit here about the number of operation that we do for a particular system. How do we compute these type of operation? So as you can see here, we have filter 1, we have filter 2 in this particular representation, and then we have the input, which has 3 channels. So for these 3 channels, we have to replicate the filters here for this particular channel. The same thing here so again, this should be 0 here, and this should be 0, because the filters have to be replicated for every one of these particular type of channels. So you can see here, we are applying these particular filters here, and we end up by 4 by 4 here for the output. And since we are dealing with 2 filters, so the system of the convolution here is going to provide us 4 by 4 by 2. So if I ask you the number of operations that have been provided here, so I would like you to compute for each entry how many operations have been made so that we have one particular entry in this particular tensor. Remember, the tensor is 3-dimension matrix. Okay, so the tensor here is 4 by 4 by 2. Okay, so here we have 4 by 4 by 2, which is this value, times for each one here, in order for us to capture this particular element, we have to do 3. You have to have this times filter component 1. You have this times second component of filter 1, and you have this times component of filter 3. So here 3 by 3 times 3 in order for us to obtain this point. Okay, so that's where the number here comes from. So it's 4 by 4 by 2, which is the dimension of these two output type of elements, times for each one of them 3 by 3 by 3. So I would like you to be able to know how to compute this particular number. This is also another components in CNN that you need to be familiar with. Okay, so a convolution layer in general. So once we have the output of the system here, then we pass it through what is known as rectifier linear units to make sure that the output of the system is filtered. Basically take out the negative values, only keep the positive values, and then add a certain type of bias term if you think that the bias term is going to be useful for that particular type of system. And we end up with a system which has the same dimension, but with different type of values for this particular type of entries. Okay, so this is a representation in general. So this is the input layer. So you can see 6 times 3 times 3, so 3 times channel. Usually that's an RGB image. And then we have these type of characteristics. So what the system tells us, so you have dimension of each filter is equal to 3, the stride is equal to 1, P1 is equal to 0. This 1 means that it's the convolution number 1. That's the layer number 1. S1 is layer number 1. F1 is layer number 1. And then you have these two filters. So we end up by 4 by 4 by this 2, and this 2 is no other than related to these numbers of filters. So the dimension here, basically the dimension in this particular, the width of this particular area here pertains to the number of filters. The dimension here is due to the filter size, is due to the striding, and it's due also to the padding, which is equal to 0. So in general, we don't create, convolution or whatever. We don't write it similar to what we have done here. So usually we write them in the form of blocks. In the form of blocks. And going from one block to the next is made through this particular type of parameters. From this block to this block, you should be able to compute these particular parameters. So this 17 by 70 by 20 comes from this and this information. Okay, so that's how we compute this thing. This and this provide us with the information here. Okay, so here, so this one, so provide us with the information here for this particular element, for this particular block. The same thing here for this particular block, and then we flatten it. So basically, we have, when we say flatten, so that's the last convolution layer, because we need, now from a matrix or a tensor to a vector. Okay, so that flattening, it means that we take all these particular elements for each one of the filters here or this particular output, and then we flatten them. So it means that we take this element here, we take this element here, we take this element here, until we exhaust from the first layer to the second layer to the 40th layer. So that now if you compute 70 times 40 times 7, it provides us with the value of 1960. Okay, and then we use an activation function that is going to be the activation function for the output predictor of this particular system. It could be several logistic functions if we are dealing with a particular classifier. So I would like you also to remember this type of visualization, and these are some of the questions that I received from some of the students, because the lecture was not recorded, and I would like to go over it because there are these particular type of element. So there are several, talk about the dense layer and the flattening layer. So also these are mentioned in assignment number 3. So the flattening, it means that you go from this matrix or tensor, as I mentioned, to vector. So this is what is known as flattening. So it becomes one particular vector. And fully connected layer here, this is going to be every neuron in one layer to every neuron in another layer. So this is what is known as fully connected layers for the system. Okay, so that's what I wanted to mention. I spoke about these particular elements last time: regularization, for dropout, for batch normalization, data augmentations are all elements that we utilize in order to improve the behavior of the system. So these are self-explanatory on the slides. I don't want to go over them a lot, but basically, randomly, we take some of the activation functions. Usually, we don't take them randomly, but we would like to visualize whether these activations function have been activated or even their activation is very low, and we take them out from the overall type of network. Remember that we have seen in assignment 1 that when the number of data is small, then you don't want to have large number of nodes in the system, because the system is going to memorize that rather than generalize. So the dropout is related to that. So it would help the system to avoid overfitting. Let me take a few questions here before I go further, please. So if you have any questions, I will be happy to respond to you. You can speak. You can utter your question if you would like, and I will be happy to respond to it if you don't want to ask the question, if you don't want to write the question.
Hi, Professor. Yeah, I had a question concerning your pooling layer.
Yes.
If you could go back to your
sure.
the convolution layer slide, please.
Yes. Tell me when to stop.
I think it's got the 4 convolution layers. I don't see the numbers on the slide, so I think it's a bit.
This one?
Yeah, if you could, no, the next one, please.
Oh, the next one. Yeah, this one.
No, the next one. It's got the 4. Yeah, this one. Yeah,
yes.
Perfect.
Okay.
So I had 2 questions. So the first one being, does the same formula apply for a pooling layer as well for the dimensions? So
yes. So yeah, that's a good question. So here what we have. So here I have shown only the convolution layer. Of course, the convolution layer has, after it, there is what is known as the subsampling. So subsampling is not mentioned here. Okay, so to be clear, very good question. So these I am talking about convolution layer. Subsampling, when we speak about subsampling, it means that this particular convolution layer itself is going to be reduced in size. So this particular 37 by 37 by 10 is becoming, let's say, 25 or 24 by 24 by 10. So the last dimension of the pooling layer during the pooling layer is not going to change. So that number, the width is not going to change. But what is going to change is this, because of the subsampling. So in this particular slide, good question, we don't have subsampling. Okay. But in general, when we are talking about convolution, then there is what is known as subsampling. So if you would like to go to the first page, to the first slide here, let me go back. Look at this one. Remember? So this is the C1 feature map. After that one, so this is where the filters have done. This is the first convolution. Then we go through the subsampling. But look what happened. This number remains the same. But here we have the subsampling. Okay? And then once we have the pooling, then we are applying another convolution. And then we do subsampling. So usually, naturally, we have convolution, subsampling. Subsampling occurs with the pooling layer.
Okay.
Is this understood?
Yep.
Excellent.
And yeah, I think a follow-up question would be, like in, if you could, again, go back to your convolution layer, please.
This one here?
The next one?
This one here, huh?
Yeah, so, in this one. So, and the other question I had was the bias question. So bias is only used in the convolution layer, not in...
Yes, exactly true. So I did not want, this, of course, I took it from the internet, this image, but we apply the activation function, so it doesn't change anything in the dimension. The only thing that it changes is the values within these particular type of tensors. So if the value here is negative, then the ReLU function is going to make it either 0 or positive if you are adding type of bias. Okay?
Okay.
So that's what we do. So we apply for each one of the convolution layer. So we are applying the pooling and we are applying the activation function. Okay?
So yeah, I'm just trying to understand the essence of the bias. So why do you use a bias in the first place? You know,
yeah, so what happens, sometimes we don't like to have very sparse functions. What is that? When we are utilizing the ReLU function, and this the value is negative, what happens? So the value is becoming equal to 0. Because remember, the ReLU function, it's behave like this. So if your values are negative, then this part becomes equal to 0. So sometimes we don't want to have a lot of sparsity in the function because we lose of the information. So what we do, we add a certain type of bias to make sure that these values are going to migrate to certain type of positive values here, and we increase the values that are already positive. Okay?
Oh, okay.
And in general, it doesn't change much in terms of the thing, but it kills that sparsity in the matrix. We don't want to have a lot of zeros in the matrix because that might affect later on the classification or the prediction type of component in the system. Okay?
Right. Okay, and I think last question, I'm sorry, I had was the filters. So I think from my understanding of like a CNN is we don't extract the features explicitly. It's deep learning, right? That's the essence of deep learning, is to extract dominant features.
Exactly.
But these filters, are they provided by us, or is it randomly generated by the system when it's learning? Or
not randomly generated. So a lot of the times, I mean, there are what is known as transfer learning. I was going to speak about it, I mean, today. So where people, I mean, for particular type of images, what you do, you take a template, you take a ready-to-go system that has already the weight set up for it and everything. And then you inject to it the image, and then the system is going to be trained and it's going to update them. So you don't do all of this yourself, okay? And as you can see in a number of libraries that you obtain, I mean, from TensorFlow, from Keras, from PyTorch. So all of these things, I mean, they are already built into this particular type of system, okay? So you say that I would like to apply this type of filters, I mean, at this particular level. However, for particular type of problems for which you have started, and the problem you know that this is not related to object detection or image recognition or something of complex type of nature, then it's better for you to start from scratch and then to play with certain type of filters that you know will provide you with a higher level of information of that particular type of system. Okay? Yeah,
makes sense. Right. Thank you.
No problem. Okay, any other questions before I move on here? Okay. So
hi, Professor. I just had a brief question.
No
so yeah, with regards to that, the filters in the CNN, would like each element within that filter be a trainable parameter?
You can do that. Yes, there are some libraries that allow you to do that. In some other type of libraries, they are fixed. I mean, these type of filters are fixed. So to extract certain type of edges, to do certain type of functions about the function. But you could have them trainable type of filters. And there are parameters in these particular type of libraries that allow you to do that.
Okay, thank you.
Okay, no problem. Okay, so let's move on. So I have spoken about these particular type of parameters last time. So I spoke about the dropout. We spoke about batch normalization as another type of elements for the system. And I spoke about the batch augmentation, where you improve or the data set of your system by having the picture centered into various type of locations. This will enrich the extraction of the various type of filters of the model. So all of these type of things, I mean, are made to improve the behavior of the system and to lessen the chances for overfitting. So these are the type of activation functions. So we are familiar with this one. We are familiar with this one, tangent hyperbolic. And this is the one that I just mentioned to your friend, where the system gives you 0 for negative values, and it gives you the exact same values for the values for when they are positive. So these are functions that are utilized. So mostly this is utilized during the deep learning behavior, this one and this one and this one are used for the fully connected type of network for the system when we are implementing the model. This, the linear one, of course, it's utilized for the output of the system, and this one sigmoid, it's for the intermediates or the hidden layer of the fully connected system. The same thing for tangent hyperbolic. Sigmoid and tangent hyperbolic are infinitely differentiable type of function. Okay, so the objective functions for the system, there are a number of objective functions. So when also you look at some of these type of libraries, and I advise you to take some of these libraries and play around them. So Mahmoud has gone with you last week on, I think he went with on Keras. I would like you to look at his tutorial. So, and he used TensorFlow. Today he's going to go over PyTorch. So I also invite you to attend his tutorial, and I asked him to solve for you some of the problems. So for these particular characteristics, there are a number of objective functions. Some of them are mean absolute error. Some of them are the mean squared error. Some of them are known as the cross entropy loss. For each one of them has its own objective function and its own specification for particular type of problem. So the cross entropy loss is used as well for in signals, in images, in something where you would like to keep the invariance of the system for the particular input of the model. The mean squared error, we have seen MSE in assignment number 2, where we would like to minimize the error between a continuous mapping and the predicted type of mapping. The mean absolute error also has a similar type of capabilities as the mean squared error. So mean squared error and the mean absolute error has less operation to compute. The mean squared error is more operation because ultimately we are computing the mean squared value, so it requires more operation. So these comes from experience and from various particular type of applications of deep learning system. For the optimizers, these also are particular type of parameters. There is no, differentiation between all of them. Some of them might provide you better results than others, especially for the performance index of the system. So you have to test them out, and these come with experience. So there is what is known as the ADAM optimizer. There is the stochastic gradient descent, the ADAGRAD, the RMS prop. So all of these are commonly utilized optimizers, and they don't have specific preferences. It depends on the application. So I urge you, when you are doing these type of investigation, to check on these particular type of optimizers. They come ready to go for various type of libraries. So if you would like to check on certain type of performance index in terms of the value of the, of the output of the system, and also in terms of the computational resources, because those become very, very important, check on some of these type of optimizers and utilize the one that provide you the best possible performance and the best possible time of usage. Okay, and of course there are major issues in the area of CNN, so it's not an absolute better solution. And this you can discover it from assignment number 3, assignment number 2. Third problem, so you can investigate some of these particular issues. So there is what is known as the vanishing gradient. Vanishing gradient problem is an issue whether with the multi-layer perceptron or also with the deep learning type of systems. So especially when we are tackling the fully connected type of network at the end of the layer, so we sometimes we confront this particular issue of the vanishing gradients. What it means, vanishing gradient, of course, when we go from one layer to the next layer to the third layer, we feed the neural network on the feed forward type of direction. And then when we go back, as soon as we start, going back the first layer, the second layer, the gradient becomes smaller and smaller. After a while, they become extremely small, that the weights update becomes non-meaningful, and they become values that are very, very close to zero in terms of the change of the weight. So the system in these particular cases, you might this might occur when we are dealing with the small values of the weights and small values of the input type of data to the fully connected layer. And why this is happening? sometimes when you are feeding the deep learning components. And if you don't utilize these type of ReLU function with the bias, and if you have a lot of zeros in these particular type of functions or the type of inputs, then you are going to be stuck with this particular problem of the vanishing gradient. That's why the bias term is very important for those ReLU function. Overfitting is always the same problem. So if we don't do very good regularization of the system, then the system is going to memorize what it has been trained with. So this applies to MLP, it also applies to CNN. The only difference here is that for the MLP, you are confronted with a huge type of input. So for instance, if you have an image of 1,000 by 1,000 pixels, you are going to end up with a million entry as a feature attribute for the multi-layer perceptron system. Imagine a million entry, and then your output will be possibly to classify between the dog, the elephant, and the cat. The output is 3. Imagine that if when you are going through the hidden layers of the system, imagine how many weights you are going to create for this particular system, especially when you don't have a lot of data. Then the system becomes, incomprehensibly large, and the system is going to do overfit, is going to be non-good generalizer. So that's why we utilize deep learning system. What deep learning system does, first of all, it provides you with the capability of having large number of images where you have these particular animals in various type of position, in various type of setting, and still you can recognize that animal because the kernels that you are going to apply are going to be invariant with respect to that particular image. That's one thing. Secondly, the outcome of the deep neural network, you could control it by the number of filters that you are utilizing and by the size of the pooling type of layer for your system. So you can reduce them as much as possible. You can play with them. So instead of having a million input attribute for a multi-layer perceptron, you can end up with 5,000 or 1,000 for the deep learning system. So still the overfitting is a possibility if you still have very large type of outcome when you are flattening your system. So the overfitting is still a problem for the CNN. And that's why we do regularization for these particular type of systems and reduce some of these type of nodes from the system. So this, I wanted to mention it because these are some of the problems in this particular system. So this is, what we mean by the vanishing gradient. So as you can see, we start from the outermost layer of the system. So the gradient start large and then become small, 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 small until you reach this particular area here. And the delta W becomes extremely equal to 0. And you feel that the W here doesn't need to be updated anymore. But that's not correct. That has happened because you had a vanishing gradient. So try to make sure that the gradient doesn't vanish as it goes from one layer to the next, to the next, to the next. So this is very, very important. And this is, very valid type of issue in the area of vanishing gradients. There is also the other issue where the gradient is becoming explodingly large. When the gradient becomes extremely large, when, for instance, the input of the network are very large, they are not calibrated between, let's say, between 0 and 1, then the gradient becomes extremely, extremely large. We would like also to avoid that because when you are dealing with extremely large gradient, then you are falling into similar type of problem. The model of your system is becoming unstable. So try to avoid vanishing gradient and exploding gradients. In these type of libraries that you utilize, those professional type of libraries, there are a lot of mechanisms that people have invented, and they have, accommodated these type of libraries to avoid the exploding gradient or the vanishing gradients. And there are even certain types sometimes of warning that the system tells you that your result might not be reliable because you have this particular type of issues for the vanishing gradient or the exploding gradient. Overfitting, of course, I just spoke about it. We are very familiar with it. So we have here, I mean, a major variance between the training type of data. So the system is memorizing, the system is not generalizing. This is a good fit. This is a robust type of output system. This is underfitted. So this is large bias, as we have seen in problem 3 of assignment number 2, in the various type of example I have shared with you. So try to avoid this. Try to avoid this when you are dealing with these type of systems. So the vanishing, the exploding, the overfittings are problems that people have encountered with CNN. So let me tell you here, I mean, there were major discoveries on CNN starting 2012. I mean, as I mentioned to you, with the major achievement of AlexNet for classifying the CFAR type of images and the MNIST type of images. And then there were major discoveries here. So the VGG type of network, the network in a network type of things, they were discovered, I mean, certain number of years ago. The Inception V1 type of network, the ResNet type of networks, I mean here, the exception network, the ResNet TS, each one of them, each one of these type of network has a particular type of structure. It provides you with the number of convolution layer. It provides you with the number, with the weights for the system. So some students that are, I mean, in their mid stage of their type of research, for these type of network, this is Inception 3, they know that their problem is related to the Inception V3 for classification or for prediction. So what they do what is known as transfer learning, and they use the exact same architecture of that particular network in order for them not to spend a lot of time. So you find these Inception networks, I mean, Inception V4, Inception ResNet, all of them, you find them in the literature, and they are provided in certain type of libraries. So these are major type of discovery that have been made. And if you can see here, as I mentioned to you, LeCun has provided one of the earliest type of network, the one that I showed you in the first slides of this set of slides. That's LeCun net, that is known as the LeCun net. It was in the 1990s. Okay, so these are the developments, and as you can see, things started to explode from here. Okay, and since then there are major type of discoveries in all these particular type of areas. Okay, so this is again an overview of what has happened, historic architectures and what's happening. So the LeNet, as I mentioned to you, AlexNet, it's the one that has made the, I mean, this type of discovery, the VGG16 net. And these are modern architecture after 2015, 2016. All of these have been implemented, and GoogleNet, I mean, is also one of the major type of network that have been utilized in wide range of application over the past few years. So if you look at the LeCun net, I mean, this is the one that was described in 1998, and it is this particular work. By the way, this particular work is the child of the work that has been started by the LeCun and Schrödinger in the early 90s. They started talking about this type of convolution layer in the early 90s. But this is the first one that he has utilized to identify handwritten digits for the code. And the system has performed extremely well. The only issue is that during that particular time, 1998, we did not have GPUs, we did not have clouds, we do not have computers with large amount of memory. So in order for LeCun to solve this particular problem, he used, I mean, supercomputer at the time. And people said that while the results are excellent, these type of results cannot replicate it. So then, I mean, this study has remained there for almost 12 years until the advances of this particular area. Remember this particular area, remember NVIDIA, remember the cloud, remember Hadoop, remember all of these things, I mean, started in this particular area. And that explains the explosion in the interest of convolution neural network, and things haven't stopped since then. Okay, this is another network. So this is exactly the network that has made the success of what we call deep learning system. So this was made by Alex Krzyzewski with his students of a colleague of ours at the University of Toronto by the name of Professor Hinton. So he worked with him on this particular network, and this is the network that provided the success of deep learning in 2012. There was a benchmark that they have been able to break the records for recognition of images using this particular type of structure. So this is what is known as the AlexNet. And if you go into the libraries, you find, this particular structure with all these weights, so you can do the transfer learning from this particular system into your own network utilizing this particular structure. So this is the magic structure that made it possible. So this is where AlexNet. So I remember it at the time. I was reading in articles, and there is even one student from the research lab of Hinton and one professor who came and provided a presentation here in Waterloo about successes at that time about deep learning system. Nobody was, not many institutions were familiar with deep learning and what it does, but we received, we invited the professor and student to give a talk about these successes of this particular type of network. So going forward, this is, the architecture of AlexNet, and then there is the VGG16 type of network. So this is another type of structure. Okay, so it offered a deeper yet simpler variant of the convolutional structure with the smaller sizes of this particular network. So as I mentioned to you, Google has provided another type of network which is called Inception network. Utilizing Inception cell, utilizing what is known as auxiliary loss components of the system. So basically, it's a variant of CNN with various type of addition. So since 2012, people started, improving this type of algorithm and providing better type of structures. This is another type of network known as residual network or ResNet. So this is another type of network which uses what is known as the residual type of connection. If there are some of you who are interested in this type of network, please email me, and then I will provide you with some seminal work related to this particular type of network. Okay, another type of network, the ResNet, XT here, it has provided also additional type of architecture and improvements of architecture for the system. So these are variants of the very usual type of network. So this is another modern architecture of the system known as DenseNet. Also, instead of having pooling layer of the system, we utilize what is known as the dense block between the various type of convolution layer. So we utilize the pooling layer after the first type of convolution in order to reduce the size. Again, the pooling, is utilized to reduce the size of the convolution type of output, and then we can utilize several type of dense blocks. So we can up to 4, 5, 6. I think the largest one that I am familiar with is around 10, dense block 10, and then the system is able to protect it. This is especially for objects that are in motion, that are, similar to the horse. So the horse standing or horse walking provide you with the representation of a particular type of horse. Of course, as I mentioned to you, there are a number of aspects in these type of neural network systems. There are what are known as the tuning parameters. So while we are familiar with a number of libraries for these particular systems, and they are very well suited, there are also some issues that we need to tune for this particular neural network. That's why my advice to you, if you have a particular problem, if you have you have been assigned a particular problem to solve, then look in the literature of the best type of network in terms of computational resources, in terms of implementability, and in terms of the various type of library that have been utilized for that particular system. Look at it, try to contrast your problem with that particular problem. Because problem for video recognition is different than problem in image recognition, is different than problem in object detection within a particular type of environments, is different than problem in activity recognition. So not every CNN is suited for all the type of problem. So you have to look at those and you have to implement them. Problem in image processing is different than problem in the area of video processing. Is different than a problem of CNN utilizing it for natural language understanding system. So all of these have different type of application, have different type of problem. Okay. So tuning CNN is, the last part that I would like to speak here. So this is what we call the hyperparameters. So they could be in the tuning, in the optimization library that you are utilizing, in the various type of regularization procedures. So those, all of them are what are known hyperparameters, similar to what we have seen in the multi-layer perceptron. Okay, so problem number 3 of assignment 2 should provide you with some insights about all these particularities for these particular systems. Okay, so I will take a few questions here before I go and spend a few minutes on recurrent neural network systems. I will be happy to take any question here. Okay, so if not, so let me jump and let me sharing this option here. So let me here share content. Okay, so let me go here and then I start. Okay, so let me speak a little bit about deep recurrent neural network. What are they? Why do we do them? And why we utilize them? Okay, so let me do this and let me share the material with you. So let me share. Where is sharing the material here? Let me share this. Share content. So where is my content here? So the content that I need to share, I believe, is this one. Yeah. Okay. So recurrent neural network. So this is not part of the midterm of the quiz. Everything that we spoke up to now is part of the quiz. So you need to prepare, you need to look at all these examples and to understand all these type of aspects. So what are recurrent neural network? What are recurrent neural? Recurrent neural network are no other than, type of neural networks, but with an architecture where the signal, instead of going forward, the signal from one particular layer to another layer could go backward, and it could feed particular type of layer that we are located at this particular level here. So please differentiate this from the backpropagation learning algorithm. Backpropagation learning algorithm doesn't mean that the structure of the network backpropagates, has back layer, an information that is fed backward. It is used for the learning procedure. So here in this type of the neural network, we are dealing with systems for which the particular states that we are at this particular stage depends on an earlier value of the network. An earlier value of the network, what does that mean? It means that it is depending on a signal that has been processed few minutes ago. Remember, let's suppose that we have a horse, and this particular horse is walking and suddenly it stopped. Let's suppose that we have snapshot of that particular horse. Snapshot, and you took the horse when it is, this particular instant, and you see it as a steady horse. So it's, steady horse, so it's not showing that it is running. So how can I tell what type of activities this horse was doing a few moments ago? In order to do that, we need to get some information that has to be fed to the network to tell us what that particular horse has been doing a few seconds ago. And the best example is to bring the picture that has been taken about that horse few seconds ago. Was that horse, sitting around there? Was that horse walking? Not walking, but running? Was that horse, was there a person on top of that horse? So we need to decipher not one single shot information, but a whole set of information. This is an extremely important area in the fields of deep learning system and in the area of artificial neural network. How can we do that? We have to design what are known as network with memory, or what we call them dynamic neural network. Why it's dynamic? Because it gives us some information about the current state, and also it gives us an information about state earlier and other type of state earlier, so that we are able to grasp what that particular system has been doing. So this is in the area of activity recognition. This is in the area of speech recognition. In order for you to understand what I just said, your brain has been memorizing exactly few words ago. In order for my sentence to make sense, you have to have what I just mentioned in terms of the context. Because if you heard only the word context and you keep it there, context of what? What am I talking about? I'm talking about recurrent neural network. So this particular system that has to capture information, it could go back up to 2 words, it could go back up to 10 words, it could go back up to a full text in order for you to recognize the context. This is a very important type of information that the system is able to do. And this cannot be done utilizing, simple convolution neural network. Convolution neural network are very beautiful type of networks for recognizing static type of images, for recognizing animals, for recognizing digits, for recognizing things that are steady at that particular element of time. But we have to compound them with certain other type of activities. What has the system recognized few seconds ago? What the system has done few moments ago? And that goes into the realm of what is known as recurrent neural network. So recurrent neural network form a class of models that doesn't make this assumption about the data. The data is not static. It's not, identically distributed by one particular model. So the most prominent example of such data are speech and text, where knowing a word in a sentence alter the distribution of the surrounding words so that they cannot be in arbitrary words. For instance, when you are typing on your Google system or on your Android system, the system is able to predict what is going to come next. How does it do that? Does it do that? The system predicting what is coming next because the system knows what you have written this instant of time. It knows what you have written few instant of times before. So it is able to predict what is going to be your next wording, either from certain type of rules or from certain similar text that you have written in the past. So this is very, very powerful, and these people are utilizing what is known as recurrent neural network. Okay. So a speech recognition system converts sound signals to text. Assume that we have such a system that can somehow segment a signal into a set of signals, each corresponding to a word. So the system is operating in real time, and at what point has predicted the following sequence of words. She placed the pen on the. So the system has to predict the next word given its corresponding signal. So when the system is extracting from the signal what the system has conveyed, the system has a certain type of likelihood of what is this particular word. So the system might, if it has a certain set of candidates, so the pen on the table, the pen on the desk, the pen on the kitchen. So even from the sound of it, the system is not going through the extreme detail of understanding all the sounds of that word. So if it understands the sounds of the desk, it means that it's the desk, basically, or the desktop, or something of that particular word. So that particular word is understood through the context and through the previous type of context. So the system is understanding the context of the word that you would like to fill up there, or the speech recognizer is doing it. And this is basically has helped a lot in terms of improving speech recognition over the past 10 years, and of course utilizing a huge amount of data for training these type of systems that the system has maybe seen in previous type of circumstances. For instance, given the context, she placed the pen on the probability of seeing cloud for or the next should be low. So the system has certain type of likelihood for words. So even if you have minor recognition confidence level for the work desk is better than the work cloud. The work desk is better than the work for. So if the system is going to do this type of comparison, the system is going to scan according to the context of that particular type of sentence. So that's how these type of things work, and that's how they do the prediction for this particular system. So this particular system work with what is known as the delay components for the system. So this is what is known as the folded recurrent neural network. So we are not going to go over the details here, but this particular hidden layer for the system is connected with the input through this particular type of hidden layer. So between this input to this particular hidden layer. But look what happens here. This hidden layer is connected with another hidden layer from past instances that is going to give it some information that it requires it at this particular instant of time. So when the system has recognized that you are speaking about a particular utterance, the system is going to make the connection, the mapping between this element to this hidden layer, but it is going to also utilize this delayed type of information that the system has recognized a few moments ago, and it's going to share it with this hidden layer so that the hidden layer with information coming from here is going to provide the output information so that the system is memorizing, is remembering, not the memorization that we showed we need to avoid. That memorization is the memorization in learning. We don't want the system not to generalize. This is memorization of the context of the previous type of words or the previous type of signal that the system has done. So if we open that particular type of folding, and if we go from time -1 to time t plus 1, look at how these particular type of hidden layers are going to get this information from this particular instance, which is the one earlier. And this hidden layer is taking information from the earlier type of instance, so that when we are folding the neural network, we find it, all of it is embedded in this particular type of information. So this is what is known as the enfolded recurrent neural network. So I'm not going to go into the details of the recurrent neural network. I might add few slides next time I speak to you about recurrent neural network, which might be on next Friday. Otherwise, I will go over 2-3 additional slides. So this particular component is not part of the for the quiz on Monday. So before I end the lecture, I would like to give you a chance to ask me if you have any questions. So that is what I have. I will post this set of slides as well for you to be familiar with and to understand what we mean by recurrent neural network. It's a whole area on its own, and for those of you who would like to have more information about it, please let me know, and I will be happy to provide some information to you. So we still have few moments, so I'll be happy to take 1 or 2 questions, very quick ones. Okay, so if not, so then I thank you for attending today's lecture, and for next week, so we will have the quiz, and I urge you again to start working on assignment number 3. And then if you have certain type of issues, please communicate with my TAs to help you out, or you can send me email, and I will be happy to help you out. If you don't have any questions, so I stop recording here.